Okay, so I got this compiled program from running the GNU C compiler on my MacBook, and this assembly language will work on my MacBook, but it won't work on this computer that I built because this computer has its own assembly language that I sort of invented. And so what we would need to do is we would need to find a C compiler that would compile this program for this computer, but since I haven't written one, it doesn't exist. So instead what we can do is actually kind of handwrite the assembly language program ourselves. And so that's what I've done here. And so this program is basically the same thing as this, but it's written in the assembly language for this computer. And so if we want to kind of look at it just really quickly, zoom in a little bit here, help us see what's going on. But if we look at our C program again, basically what we're doing here in these first two lines is the x equals 0. Actually, we're doing the y equals 0 here. There's a little bit of an optimization that I needed to do because the memory on this program, on this computer only has 16 bytes of memory, which is not very much memory at all. And so because we needed 3 bytes left over here at the end for the variables x, y, and z, I had to do a little bit of an optimization here to make the rest of the program fit. And so the first two lines is setting y equal to 1. Let me just cross that out. This is y equals 1 is what this is doing. So it's loading 1 into the A register, and it's storing that in the E, which is y, at memory location E, which is y. And then it's this is sort of the x equals 0, except we're not really saving it, and that's just to kind of save me that one line of code. So this is sort of x equals 0, and then we output. So we're kind of doing these a little bit out of order, but it doesn't matter. And then the printf is sort of my output here. And then we do the add, and we're adding, let's see, we're adding E. So we're adding y to x. So x is in the register, we're adding y. So this is kind of, you can think of this line as being the z, well, this line here, actually these two lines are the z equals x plus y, because this store A is storing the result of this in f, which is address location f is z. So this is the z equals x plus y. And then these two lines here are the x equals y, because we're loading from E and then storing to D. So E to D is y to x, so x equals y. And then here we're doing the y equals z, and it's the same thing. We're going from f to e. F is z, and address e is variable y. And then at the end here, we load a again, and this is just, or we load the value of x into the A register, and that way when we loop back, we output the value of x. And this is kind of, again, this sort of optimization I did to, rather than storing it up here and then loading it again, that would take 2 extra bytes. So this is down here. And then the jump carry. So what this is saying is that if the result of the last addition, which is up here, had a carry bit, which means that this is an 8-bit computer, so if the result of that addition was took up 9 bits, and because 1 bit had to be carried, then go to the top. And that's kind of a way of detecting whether x is greater than 255, because if it carried into a 9th bit, then it's something that takes more than 8 bits to store is going to be greater than 255. So if that's the case, then jump all the way to address 0, which then resets the y equals 0, x equals 0. Otherwise, it falls down here, and we only jump up to address 3, which is the output. So again, sort of going back to the printf. So you can see this program is basically another compilation, I guess, if you want to think of it that way. We've compiled this C program, but instead we've compiled it for this home-built computer here. Now the next step, now that we have this assembly language, is to convert this to machine code. And so I've done that here, and slide this over so you can see everything. And so what I've done here is this is the same program that we just walked through, and what I've done is just converted everything to binary, because when we program the computer, we're going to be using these switches, and we have to enter these things in binary on these switches, which is very cumbersome, but fortunately it's a short program. And so basically the addresses here are just 0 through C hexadecimal, which is 0 through 1100 in binary. And then each of these opcodes here, each of these instructions has a corresponding 4-bit binary value, and so I've just substituted those in here. And then most of these instructions have some sort of parameter that goes with them, and then that is just converted to binary over here. And so this is what we'll go ahead and enter. And so let me just kind of slide this over a little bit so we can get it right next to here and zoom in so we can see what's going on. And so to program this, I'm going to stop the clock real quickly and just clear everything out of the computer, and then we'll switch it over to programming mode. And so in programming mode, what I can do is I can set the address, so this is all zeros, and then I can set down here the data that I want to program in, so 1, 1, 1, 0, 0, 0, 1. And then once I have that programmed in, I'll just push this button to program it. And then I can move on to the next value. So this is memory location 1. And it's going to be, let's turn all those off, it's going to be 0, 1, 0, 0, 1, 1, 1, 0, and I can program that. And I'll go ahead and program the rest of this. And through the magic of video editing, we can speed this up for you. And there we go. So I think we're all programmed here, so we can go ahead and shift that back into run mode, and I will zoom out here so you can see what's going on and get this here. I think you can see everything there. And so now we can reset the computer and try running this. And it looks like it is working. Yeah, here we go. It's counting through all the Fibonacci numbers. And it looks like there might be a bug. It looks like it's missing the last one, the 233, so there's probably a little bug with the jump logic. Maybe I'm, oh yeah, because I'm outputting first and then adding. Okay, well, maybe I'll fix that a little bit later, but it's close enough. We're getting Fibonacci numbers.